exponential and logarithmic models. Now we're going to take our exponential equations and we're going to use them in order to solve. This is different from another section in the fact of we're going to be able to put variables wherever we want because we have all of our solving properties that we've learned along the way. So when we're looking at exponential growth and decay equations, most oftenly we are going to use the continuous decay equation or this continuous equation here. And so when you're looking at it, this one right here is the one we want to use. So use this one. It says a certain bacteria population is known to double every 90 minutes. Suppose that there are initially 80 bacteria. Write an expression that models the size of the population after T hours. So let's figure out what kind of information that we have. First of all, it says that a certain bacteria is known to double every 90 minutes. It's important to note here that we're looking after T hours, so we do want to change this to 1.5 hours because we want everything to be in the same unit, and they're telling us that our expression needs to be in hours. We also know that we initially started with 80 bacteria. So if I start with my equation, f of t equal to a e to the rt, my initial value, that's always my a. So this would be f of t is equal to 80 e. Now, I do not know r or t. We are going to represent the expression after t hours, so t will be in the remaining part. What we need to do is figure out what r is, and that's where the doubling every 90 minutes come into play. So let's just kind of write out what we're looking for here. So we want to find r from doubling time. And so that means when 80 bacteria are doubled, we have 160 bacteria. Our initial was 80, e to the r, and that happened after 1.5 hours. So we're going to solve this for r. I'm going to divide both sides by 80. It gives me 2 equal to e to the r times 1.5. My goal is to solve for r, so this is where our log properties are going to come into place. Because it's an e, I'm going to ln both sides. That gives me ln 2 equal to ln e to the r 1.5. ln e cancels, and my properties of logs, that exponent can also come out front. Now, when we say that it cancels, it means that you're looking at ln 2. I can bring that 1.5r ln e out front. ln e, remember, that's your inverse property. That equals 1. So that's why I'm saying that that cancels. And then I'll divide both sides by 1.5. So that gives me that my r value is equal to ln 2 over 1.5. Now, all of these rates and these numbers, these are not going to be nice numbers as we work through here. So we're not going to let that stress us out. Our goal was to write an expression. So I'll just take what I already had go in here. 80 e to the, now my r is ln 2 over 1.5 to the t. So now if I want to figure out what is the amount of bacteria I have after how many hours, I can just plug in for t and I have my rate of how this is growing. Let's keep working through some examples. Really, the main point of what we're going to look at here is we're going to work through some different situations. What information is being given, and then how can we fit that into the equations that we know. The next one says the half-life of radium-226 is 1590 years. If a sample contains 200 milligrams, how many milligrams will remain after 1,000 years? So let's kind of do some key takeaways here. With this situation, we know that the value of the sample is 200 milligrams. It says if a sample contains 200 milligrams, so this is our initial value. So I would say f of t is equal to 200. Again, we're going to be using that ae to the rt, e to the rt. Then I'm going to try and figure out, like we did before, we're going to find our rate or find our r value. So we need to look back through the problem and find the information that's going to help us with a rate. And we see that the half-life of radium is 1590. So that means if I start it with 200, I'll have half of that, which is 100, after 1,590 years. So you can see the setup is the same as the previous example. So again, I'm going to solve for r. So I'll divide by 200 on both sides. I get 1/2 equal to e to the 1590r. I'll do the same thing as I did before. When I ln both sides, ln e cancels. And I get ln of 1/2 equal to 1590r, and then I could divide. Again, I'm not going to be shocked that I got a similar situation for my r, and I'm not going to run to my calculator and grab that decimal. I am going to leave it as that fraction. So the completed equation would be 200e. My rate is ln of 1/2 over 1590 to the t. Now this one did not tell me to write an expression, but I do have an equation. Now I can answer any question that remains about the situation. It says how many milligrams will remain after 1,000 years. So that means I now have something I can plug in for t. So step 2, I'm going to plug in t equal to 1,000. So it gives me 200e. I'm going to say ln of 1/2 over 1590. My t is 1,000. And when you're plugging this into your on-screen calculator, you want to type it just like this. And that would give me, now I'll round, 129.331 milligrams. And so you can see very similar to the first part, except this time I'm looking at actually calculating a future value, or in this case, how much will remain after 1,000 years. 2 more examples. It says a wooden artifact from an ancient tomb contains 35% of the carbon-14 that is present in living trees. How long ago, to the nearest year, was the artifact made? The half-life of carbon-14 is 5,730 years. And so this is what we want to start with. The fact that it told us the half-life is 5,730 years. And so just like in the previous 2 examples, the first step we're going to do is we're going to find our rate, or our r. Now this one's a little tricky because you'll notice we don't have a starting value. We just know what was left when we looked at the artifact. And so even though the emission amount is not given, we can still find our r, because we know that it's a e to the r, and this is after 5,730 years, and that half of it is left. So half of whatever my initial value would be left. And I'm not concerned that I don't have that initial starting value, because my goal is to solve for r. So when I divide both sides by a, that a cancels. I'm left with 1/2 e to the r, 5,730. I'm going to ln both sides. And that gives me ln of 1/2 equal to r, 5,730, and divide. And so you can see, even without that initial amount, just knowing what its half-life was, I could figure out my rate. Now, step number 2, now we need to find our t value when 35% remains. So I know that the wooden artifact has 35% of the carbon-14 that we just calculated our rate with. And so I know that, again, I don't have to know that initial amount. So I don't know the initial amount, e. We just found our r. So that's ln of 1/2 over 5,730 t. And we know that 35% of our initial value remains, so that's 0.35 times a. So again, like I did before, I could divide both sides by a. I get 0.35 equal to e ln 1/2 5730 t. And then I'm going to do like I did on the left side there. I'm going to ln both sides. So that cancels out my e, and I get ln of 0.35 equal to ln of 1/2 over 5730 t. And then I'll just divide by that value. Now, you do not want to use rounded decimals through this process, Make sure that you're using exact values in your on-screen calculator to calculate this. And this would give me 8,678.5. Or, because we're talking in years, we could say 8,679 years. So it says, how long ago to the nearest year was the artifact made? Nearest year is why I round it. It was made 8,679 years ago. There's a lot to these problems, but hopefully you're good with your solving with your logs. Using your on-screen calculator is going to help you, because I would just want to enter this right here into my on-screen calculator, then round at the end. Let's do one more. It says, find the time required for an investment of $5,000 to grow to $7,400 at an interest rate of 7.5% per year, compounded quarterly. So the fact that this is saying compound it quarterly, I'm going to go back to my equation of f of t equals a 1 plus r over n to the nt. Then I'm going to fill in the values that I know. I know that I had an investment of $5,000, so that means I'm going to have $5,000 right here. And then I want it to grow to $7,400, so that's what it's going to be equal to. And then I say I have an interest rate of 7.5%, so that's my R, so I'm going to say 0.075. It's compounded quarterly, so that gives me a 4 for my N. And then we're trying to find T. So we've done problems like this in earlier discussions, but we didn't have it where we had a T we were solving for. But now with our skill set of being able to solve for that exponential using our logs, we're able to solve a problem like this. So I'm going to divide both sides by 5,000. And that gives me 7,400 over 5,000 equal to, let's see, that would be looking at this value right here, the 1 plus 0.075 divided by 4 gives me a value of 1.01875, just to condense that down to the 4t. Now this one didn't have an e like the previous ones, but we are going to turn this into a logarithm by ln in both sides so that I can pull this exponent out front. And so that gives me ln of 7,400 over 5,000 equal to, and because it's a natural log, I can bring that exponent out front, ln of 1.01875. And then we got to remember, what's our goal in this? Our goal is to solve for that t. We're trying to find the time required. And so this is 4 times t times ln of that number. So I'm going to divide by 4 ln of 1.01875 so that I can isolate that t, but I also have to do it over here. Now, this is where your calculations, you need to be very detail oriented. Be careful. Don't use rounded values till you get to the very end. You can plug this into your on-screen calculator, and that would give you a value of 5.28. So this means after 5.28 years, our $5,000 investment, compounded quarterly at 7.5%, has grown to $7,400. So these problems are a little bit more. Take your time. Seek help if you need assistance.